At the end of the last video, we were doing a calculation to find the relative populations of J equals 0 and J equals 1 energy levels for HCl around room temperature. Looking at the slides for this next one, I had at the beginning of this class in the spring semester this question, which we did in class with the clickers, and I thought it would be a good one to leave in and give you a moment to think about. So the question says, it's a little bit convoluted there, but there's an energy level diagram over here on the right, which shows us the energies. It's got the J equals 0 and 1 energy levels, and then the numbers underneath the individual horizontal lines there would represent the M sub J values for those, right? So that reflects the degeneracies. Okay, so the question is, how would we compare the populations where the population, the N with 2 subscripts, think of that as being just J and then MJ, all right? So N11 would be the population of, let's say, that state right there, because that's the one that would have J equals 1 and also have MJ equals 1. So if you want, you could pause for a second and think about what you think would be the right answer for this question. I encourage you to go ahead and try that. Rather than just sit here and do nothing, I'm going to go ahead and hop to an explanation, I think. So the first thing to say is if we don't, without having to remember what we did last time, the single of the states that are there are 4 individual quantum states in my picture, right? Because each of those 4 horizontal lines is a quantum state. The one that's lowest in energy, which is the 0, 0 state, that one has to have the highest population of the individual quantum states, right? So that says that I could throw out, I guess, this one, because that choice says that the state above that would have more population than the lower one, and that can't actually happen. Right? The next thing we can say for sure is that the populations of these 3 here, those should all be equal because they all have exactly the same energy, right? And the population only depends on the energy, and that says that I need to have the ones that are in the J equals 1 level all have to have equal populations, and I think that forces me to choose this one here as my my correct answer. Right? Remember at the end of that previous video we calculated that the total population in J equals 1 was larger than the total population in J equals 0, but that's because the population in J equals 1 is spread across those 3 states, right? So again, it's the degeneracy that really makes it end up being the more populated energy level. All right, today we're going to start to talk about connecting the population ideas that we developed last time to thermodynamic properties, right? Statistical mechanics is, there's a sort of very tightly related subject, which is sometimes referred to as statistical thermodynamics, and that's because we can use these statistical arguments to get thermodynamic values, and we're going to start to look at how we would do that today. So, what we want to do is we want to think about how to get a thermodynamic property by averaging over all the possible states, right? And so the simplest one to start with is the internal energy. Right? The internal energy is just going to be a properly weighted average of the energies of the possible states, right? So if we set the energy scale so that the ground state is just declared to have an energy equal to 0, whether it really does or not. Right? We know there's 0-point energy in some of our models, but we get to pick a 0 in energy whenever we set up a problem, right? If you're doing a physics problem with potential and kinetic energy, you get to pick the height at which the potential energy goes to 0, for example, right? And that's really what we're doing here. We're just saying we're going to call the ground state 0 energy. That will force that U of 0 term in my bottom equation to be 0. Right? In that case, the internal energy is just going to be the probability of being in state I times the energy of state I, right? And that has to be true, right? If I were to measure the energy of a single particle, say, I would get an energy that corresponds to one of the states, and if I measured that a lot of times, the probability would tell me what fraction of the time I would get each of the possible values, right? So the average internal energy is just going to have to be the weighted average of those, where they're weighted by the populations. Right. If we take that expression and we take the expression for the probabilities that we developed last time, which is this one up here, right? That one we got last time as the probability from the Boltzmann distribution, right? And again, I'm going to set this U0 term, I'm going to call that equal to 0. That's the mathematical expression of saying I'm just going to declare that the ground state energy is where I'm putting the 0 of my energy scale. Okay, then I just get that U is equal to the sum written here, right? Where all that's done is to say that I can put those in for the probabilities, and that's all we've done there. And then pull Q is a constant, so it can be pulled out of there. And that gives, well, it's a constant at fixed temperature, right? I can take that summation and I'm going to just do a little bit of work here to make a connection between that summation and dq dt, the temperature derivative of the partition function, right? The partition function will change with temperature. We'll establish that very clearly over the course of this video, right? So I'm going to take the derivative of the partition function with respect to temperature at constant n and v, because those are the things that we're going to have fixed when we do this. That's going to be the derivative of that summation, right? Because this summation, this thing, that's q. Right. If I take the derivative of that thing, the only thing that I have the t in the exponent is the only place there's a t, right? So if I do that, I'm going to get an 1 over kt squared that's going to come down out of the exponent, and that's going to be in every term. I'm also getting the epsilon sub I here, that also comes down out of the exponent, but that one's different for each term in the summation, so it has to stay inside the sigma. This piece, the kb times t squared on the bottom, that can get pulled through the sum since it's the same for every term in that summation for all the different states. That's still the same thing, right? And that just says if I take that last equation to get from the two ends, if I take this end and this end of that one, multiply the kb over t squared here onto the other side, and that'll give me this result on the bottom here, okay? Right now you're wondering why I wanted to have that, perhaps, and so let's grab that and take it with us to the next slide. These are what we had, right? So I've got my definitions of the internal energy up here. This is this connection we just made, right? And what I'm now going to do is I'm going to take those two things and I'm going to combine them to get the expression below, right? So U is equal to 1 over Q times this expression here, right? And that expression from this one is equal to all this stuff, right? So that says I get the 1 over q from here, and I'm multiplying 1 over q by this version of this. And when I do that, I get this piece here, which says I have that. And sometimes it's handy to be in that first form. Other times it's handy to realize that because I've got a dq up here and I've got a q down there, I can write that as derivative of log of q with respect to t. And those two forms, some cases, one of them is more handy to work with, some cases the other one is. But what that last equation there shows us in either one of those forms is that we can find the internal energy as a function of temperature just by knowing the partition function, how that changes with temperature. Right? So what that does is it connects a bulk thermodynamic property, the internal energy, it ties that to the partition function, and the partition function we will come to see, we can find that just by knowing what the available quantum states are. Right? And so all I have to know is the set of available energy levels for my system, and this gives me a route to evaluate this thermodynamic quantity without having to do any sort of calorimetry or anything like that. Right? To me, it's always an unexpected result that can work out, but it does in fact, and it gives us a new path to a variety of thermodynamic functions. Once I have that internal energy, I can combine that with some other expressions to get things like, I could get H, the enthalpy, because that the definition of that is based on internal energy together with P and V, for example, right? And so I could start to put together expressions that would get me to lots of other thermodynamic properties. We're not quite ready to go and do that yet. We're going to spend a bit more time developing the ideas of the partition function before we go too much further into thermodynamic ideas. Right. So the simplest system we can try and apply this notion to is going to be a sort of a hypothetical system where we have only two energy states, two energy levels, right? So it's on the face of it seems not terribly realistic. I have a ground state and I have an excited state, and those are the only possible states. All right. There is actually a case that this reasonably applies to, and that's something like spin states. If you were working on explaining NMR spectra, you have the case that you have two different spin states, and in the magnetic field, they're at different energies from each other, right? And so that actually is a system that this two-level model can actually be applied to. But mostly it's just here because two levels is going to be a lot easier than having a very, very large number of energy levels to work with. It's going in particular to give us the opportunity to do things by just direct summation that we might otherwise not like to do that way. If we had, 10 to the 30th energy states to work with, we wouldn't want to calculate the summation by just adding up all those terms, right? So I'm going to call the ground state, I'm going to label that as E0, and I'm going to say its energy is 0. The upper state, I'm going to, in some of the equations, I'm just going to refer to it as having an energy delta, where delta is just some amount of energy greater than 0. All right, we're going to write an expression for the partition function. Then for purposes of illustration, I'm going to put a value on my delta. I'm going to say it's 10 to the minus 21 joules. Okay, that's an energy that's it's a decent energy, but it's not all that big. It's something probably on the order of a rotational energy spacing, maybe. We're going to find the chances of being in the upper state at 10 Kelvin, a very low temperature, and at 10,000 Kelvin, a very high temperature. So we're kind of developing the ideas of low temperature and high temperature limits here, which are often handy in thinking about what's going to happen to populations, right? Once I have those probabilities, I'm going to use them to directly calculate my average internal energy. Okay. The first time I do that, I'm going to do it just by saying that I can multiply the probabilities times the two energies, and that'll get me my, my average internal energy. Then I'm also going to do that starting from one of those partition function equations, just to illustrate that we do get the same result, and that it comes out shown to work, right? Again, the first method, the direct summation, that's going to work here largely because we only have two energy levels to work with, and so we don't have a lot of terms to sum up. All right, so to start putting together the partition function, my ground state has energy equal to 0. My upper state has energy equal to delta, which we're going to call 10 to the minus 21st joules. We're trying to find, say, the upper state probability at these two temperatures, right? And if I get the upper state probability, the lower state probability is just going to be 1 minus that, because those are the only two states I can be in. Right? The partition function, the definition for the partition function is right here, right? It's just the sum over all the states of e to the minus the energy over kt, right? So in this case, that's going to be the first state has energy equal to 0, so the first term is just 1. The second state has energy delta, so that says my partition function is always equal to that expression there, 1 plus e to the minus delta over kt, okay? The probability of being in state 1 is the term from state 1, which is this one here, right? So it's this piece divided by the whole cube, right? So that gets me this expression here, which if I evaluate that with the delta that I've got there, right? And I do it at 10 Kelvin. At 10 Kelvin, kt is equal to what? K is order of 10 to the minus 23rd power. So kt when t is 10 is still 10 to the minus 22nd power, let's say, right? So that's still much smaller. Kt there rather is much smaller than my delta, and so my exponent, or my exponent here is going to be such that this term comes out to be very small, right? At the low temperature, almost all of my population is going to have to be in my lower state, right? And so my probability of being in the upper state is on the order of 10 to the minus 4 at that temperature. If I go up to 10,000 Kelvin, right? At 10,000 Kelvin, my KT term now is much bigger than delta, than the piece on top, right? Because at 10,000 Kelvin, I've taken 10 to the minus 23 and multiplied it by 10 to the fourth, so I've got 10 to the minus 19. So my exponent now is very small, right? And that says that my probability comes out to be very close to 50%. Right? So at the high temperature, I've got pretty much a 50-50 chance. The populations of my two states are going to be very nearly equal to one another when I get to that high temperature limit. So the situations at these two temperatures are very different. That's not surprising, right? 10 Kelvin and 10,000 Kelvin are both pretty extreme temperatures. So we should expect something to have changed. This is my average internal energy here, right? Written in the form of an expectation value. Remember that says if we measured that internal energy of a particular particle in this system lots of times, this should be the value we would get, right? In the first instance at 10 Kelvin, it turns out that I would measure this, and almost every time I measured it, my particle would have zero energy, right? Once in a while, it would have found its way to the upper state, right? And so to find the average internal energy, all I have to do is take this population or this probability, right? Multiply it by the energy of the upper state, right? That's going to be the average because the fraction of the time that it's not in the upper state, it's got energy zero. Right? So there'd be a term there that was P0 times E0 if E0 were not zero, but I don't have to really include that term because I set the ground state energy to zero, right? So that says my average internal energy at 10 Kelvin is very, very small. There's almost no chance of finding the particle in the upper state because its chances of being there are this small, right? If I go to 10,000 Kelvin, I do the same thing. I take now my 0.498 here and multiply it times this number, which is delta. Then I've got 5 times 10 to the minus 22nd power in joules for my average internal energy. If you look at that, that's roughly half of delta. So that says when there's a 50-50 chance, if half the time I'm in the bottom state and half the time I'm in the top state, then the average energy should be right at the center line. Right? And it is now very close to the center line because I'm very close to being in the limit of going to infinitely high temperature at my 10,000 Kelvin point for this, all right? So that tells us what's going on, and we'll plot some of these at different temperatures in a moment, all right? First, I'm gonna take a look at what would happen if we tried to calculate this by using the equations for the partition function, right? And I decided not to try and write these out because it's not that complicated. If I'm talking too fast to keep up with the math, you can always pause and just take a second to work things out. But this is one of the equations that we had that says it's a route to find the internal energy from Q, the partition function, and from the temperature derivative of that, okay? My partition function expression that we wrote out on the previous slide is just this one, right? So that says the term that comes from the ground state is 1 because the ground state energy was 0. And then the second one is the term in the partition function from the upper state, right? Take those two things together and I get the partition function. I need the derivative of that to evaluate because I'm going to put the derivative in there, right? So if I take the temperature derivative of that, you should be able to convince yourselves that you just get this because I've got those terms coming down from out of the exponent, okay? And then if I take that and do some rearranging on it, I can say that I want to take those things and I want to put them in here, right? So I get kBT squared over Q, right? This thing on the bottom, that's Q. That piece is Q, right? And then I've got this piece here for the derivative, so that drops down to go there. I can do a little bit of rearranging on that because I've got my KT squared here and here. And then if I take that, I can write that like this, where that pulls the delta out in front. That's the energy of the top state. This piece in parentheses, that one actually is P1, the probability or the population for the upper state. right? And so that says I get to saying it's the product of the energy of the upper state times the probability. That's the equation I used before, right? And so I did that first by just sort of a reasonableness argument, I guess, saying, well, it's in this state or that state, and when it's in the bottom state, it has zero energy, so it doesn't contribute. This says we get that same result, even if we start with the somewhat more formal equation involving the temperature derivative and all that. So we do work out to the same spot, no matter which way we choose to do it. If I had a lot more states, then I'd be more likely to be using these equations, right? And saying I want to do that to get where I'm going. Because I had only 2 states, it probably is simpler to do it by the route of just saying, well, I can just do the sum and get what I need. So I made some graphs of what this would look like as a function of temperature. And all I did was take the equation we're working with there and put them in Excel and let it do some graphs for me. And when I do that, I get plots. And I've got 2 sets of these. This one is in the low temperature range, up to about 100 Kelvin. And then I've got one that goes higher temperature that I'll flip to in a moment. I couldn't really fit them all on the screen at a size I liked and make all that work. So here we've got the partition function up on the top, and we've got the probabilities for the 2 states on the bottom, right? If I look at these, if I start off at 0 temperature, there's no energy available whatsoever. So all of my population has to go into the bottom state. Right? That's going to be true for any system, really. In the limit of 0 temperature, the entire population has to go to the lowest available energy level. Right? When that happens, my partition function goes to 1. All right, and so in the low temperature limit, the partition function here goes to 1, since there is just one single energy state at that lowest energy level. Right? As things start warming up, gradually my partition function begins to climb. And by the time I get, if we look at the graph on the bottom here, by the time I get, say, to here, this is what, around 20 Kelvin. Once I'm past 20 Kelvin, I can begin to start to see population showing up in my upper state, right? This is the upper state population. As the upper state gets occupied, that means the lower state has to be losing population, right? Because the only way to get population into the upper state is to take it out of the lower one. Okay. If I look over here, when I'm at the right-hand edge of these graphs is at 100 Kelvin, right? At 100 Kelvin, what my delta for these, my energy of the upper state was 10 to the minus 21 joules. So at 100 Kelvin, that's about the same as KT, right? Because K is roughly 10 to the minus 23rd. Multiply that by 100, and I've got 10 to the minus 21. So my KT is roughly equal to the temperature at the right-hand edge of this graph, and that means I've got enough thermal energy around to begin to get a significant population into the upper state. And we can see that here, right? My population here is drifting up. It's getting close to 0.4 by the time I get to 100 Kelvin. And so that's kind of consistent with what we would think should happen if we use that kind of KT is the available energy sort of argument. I also have a set of these graphs that go out to higher temperatures. I didn't go to 10,000 where we did the calculation, but I did go to 1,000. Okay, and you can see that all that stuff we were seeing before in the low temperatures, that's kind of washed out now because I've stretched my scale so far. But we can still see that at 0 temperature, my partition function goes to 2, right? You can begin to infer here that in the limit of infinitely high temperature, this thing is coming up. And the high temperature limit of that partition function is going to end up being 2 in this case. That's not a coincidence. That fact that it goes to 2 is a direct result of the fact that 2 is the total number of energy states available. Right? And so that is an upper bound on how big the partition function could get in this case. You can see that once I'm getting out, I don't know, by the time I'm out around by 500 Kelvin, my populations are getting close to one another for sure. They will gradually come together, and in the high temperature limit, these things should both settle in at 0.5. Right? One way to describe that is at infinitely high temperature, all the available energy states should have the same population. Okay, that says if there's infinite energy, the best way to do things, entropy, will be the driving force, and you can spread things around as many ways as possible by getting so that they're evenly distributed among all the possible states, right? And that is what would happen. We can see that very much in the graphs for this system. Okay, so that tells us we can learn a lot from looking at that simple system where the math is not so bad. One of the things you can tell from this is you can get an idea of what physically it means when we talk about the partition function. The partition function is, like a lot of things in this course, a fairly abstract seeming idea, right? We do a bunch of math, we calculate a number. In some cases, it's a very large number, and it can be difficult to get yourself to feel like you have a sense of what that means, right? It's a unitless number, so that doesn't give us anything to try and hang an interpretation on. For my two-level system, at low temperature limit, the partition function goes to 1. At high temperature limits, the partition function goes to 2, right? That partition function is an indication of the number of states that are significantly populated, okay? A little bit of a fuzzy definition there, because what it means to be substantially or significantly populated is a little bit open to debate, right? But it's one way to describe it is it's the number of states that seem important at that particular temperature, okay? In general, if you need to take a rough guess of what a partition function is, one way to do that is to say that if you count up how many states there are that have energies that are less than or equal to kT, then all of those states are likely to have some significant population, right? In this particular system, around 100 Kelvin was where kT got to be equal to that energy gap, right? And by then we were well on our way to getting to the case where the populations were getting similar, right? They were approaching 0.4 and 0.6, I guess, then in opposite directions, meaning they were certainly of the same order of magnitude by then. Okay, that's a good way to sort of in your head have some idea of what Q means. It's the number of states that are important for the problem we're considering at the temperature we're considering, right? Because that partition function is always going to change with temperature, and in fact, it's always going to increase with temperature as things go along, right? In the case of our two-level system, we pretty quickly hit the limit where we maxed out the partition function as it approaches 2. In a real system where there's more and more energy levels to climb into, that generally doesn't happen, okay? I also want to look at the heat capacity for this system. Okay, heat capacity is a property that also gives us a lot of insight into how energy is being taken up in a system, what particular reservoirs are there that we can be pushing energy into in a system at particular conditions, okay? So to start off, think about what heat capacity means. If you were in Gen Chem and you were doing like calorimetry things, you get out your trusty old MC delta T or NC delta T equations to find the amount of heat associated with a temperature change, right? The units on a heat capacity are generally going to be energy per amount of stuff, per mole or per gram, and with temperature units also in the bottom, right? So say joules per mole per degree would be a heat capacity unit that we might see in a chemistry context where we often use moles for the quantity unit. So take that idea and write it in equation form, and we get this one here, right? That says that the heat capacity, we can define that by saying it's the temperature derivative of the internal energy, right? The subscript V here means this is the heat capacity at constant volume. There is also a heat capacity at constant pressure, at least if there are gases involved. Those two things are generally somewhat different from one another, okay? So we will generally focus on CV, the constant volume case here, right? We had this equation down here we put together earlier. So if I know that the definition of C sub V is that it's the temperature derivative of the internal energy, and right here I've got two equations that tell me the internal energy as a function of temperature, I can use those, and all I have to do is take the derivative of one of those, and then I will have an expression for the heat capacity. Okay, so that's what we've done here. And if I look at this one, I can take that, that derivative, and if you like, you can kind of work through that and get that these are the results. But if I flip back for a second, I'm working with, I guess, I'm working with this piece here, I think. And if I do that, I'm just putting in the Q expressions in its their respective places. Right, and when I do that for my two-level system, I could get to what I've got stretched out here, right? So although the expression up here looks a little bit involved, I've got this piece out there, which is just delta squared. That's the energy spacing again, of course, over KT squared. I've got this set of terms here. That's the probability of being in the upper state, right? And then I've got a set of terms over here, which is either 1 minus P1, or that also makes it P0, right? So I can relate my heat capacity to the fractional populations of my two energy states. In this instance, it's relatively simple to do that. Again, that's because we only have two states to work with, right? If I had a system with lots and lots of energy levels, then I'd have a lot more work to do to try and break that down into those probabilities. But in principle, I could still do that. I would just get a lot less convenient of an expression, okay? So using that, that result, I've again plotted up what happens to the heat capacity as we walk through a range of temperatures, okay? And so here I've got this, again, plotted in two separate graphs. Let's look at the axes. I've got temperature on the x-axis on both. The first one goes from 0 to 100 Kelvin. The second one goes from 0 out to 1,000 Kelvin, although much of that graph is not of interest because the heat capacity has kind of come back down to 0 for the second half of that path. The y-axis in both cases is C sub v in units of Boltzmann's constant, okay? Boltzmann's constant, remember, has units of joules per degree. So this is the heat capacity per molecule rather than per mole, right? So you think of your heat capacity as being, say, maybe joules per mole per degree. This one is joules per degree because the unit of quantity here would be just molecules rather than moles, right? That's a little bit of an odd thing. But the same actually works in the gas law. You can write the gas law if you replace R with K. Then N goes from being the number of moles to being the number of molecules, and you still have an equation that works if you do that, because one way to think of Boltzmann's constant K sub B is that it's the gas constant per molecule. Right? If I take these and look at what's happening, in very, very low temperatures, down here near the low temperature limit, my heat capacity starts out essentially at 0. That's because if I don't have any energy available, I can't get any molecules. I have no chance of moving the molecule up to the upper state, right? So I have to have enough energy on hand to make it viable that the molecule could climb to the upper state, or that if I had a lot of molecules, that at least a few of them would make that upper state. Right? And in very low temperatures, that doesn't happen. And so I get my heat capacity stalled down near 0 until I've gotten some temperature into the system. Once I've done that, I come up and my heat capacity clearly goes through a maximum here. And it looks like that is somewhere around 30 or so Kelvin, right? At that point, it's getting much easier to move molecules, move population from the lower state to the upper state. Right? I also still have lots of room in my upper state, right? I could still raise that population quite a bit, right? In this case, once I go, by the time I'm out here to 100 Kelvin, I'm falling significantly, my heat capacity is, and by the time I get to 500 Kelvin over here, my heat capacity has come back down to be pretty close to 0. What's happening there is that I've gotten to where the populations of the upper and lower states are nearly equal, right? My probabilities are roughly equal. I can never get to where the probability of being in the upper state is higher. Right? That would mean if you actually did that, if you made the upper state probability be higher and you took the equations and solved it for the temperature, you would get a negative absolute temperature, right? And that's not a physical thing that we can have. So that's not a possible situation, right? So in this case, because there are no more higher energy states, my heat capacity gets locked in and in fact comes back down to 0 because once my system is close to 50-50 population, then it can't take up any more energy. Right? It has no further capacity for taking in energy. That's a bit of an anomalous result because we concocted this simple system with only the two energy states to work with. All right, but that is how the math will turn out. And again, I made those graphs just by taking the equation that's on the previous slide and setting it up in Excel to let it plot a decent number of points in them and generate the graphs for us. All right. To finish out this segment, I'm going to say a few words about the transition from thinking about a particle or a molecule to a collection of molecules. Okay, we calculated the internal energy here by thinking essentially about a single particle. If I call those P terms, P0 and P1, if I call those probabilities, right, I said, well, there's this % chance the particle's in the ground state where its energy is 0. The other piece of the probability is in the upper state where its energy was delta, and I use that to calculate things, right? If the particles don't actually mess around with each other, interact with one another in any way, don't have any influence on each other, then what would happen is, excuse me, my throat's a little scratchy here. What would happen then is if we did those things, we could do this with lots of particles, and what we found would just be the average of those lots of particles, right? So the total internal energy, if instead of having one particle, if I had 10, my total internal energy would just be 10 times as large, right? Because every particle was playing by the same rules. And so I can use the same ideas, the same arguments, the same equations. I've mentioned that a couple times when I've said, well, I can talk about those P terms as being the probability for a particle or being the population or the fraction of the particles that occupy a given state, right? And that has to work out both ways, okay? Strictly speaking, the partition function, the way we've been writing it, is when we write that uppercase Q, that's the formal name of that partition function is that it's the canonical partition function, right? The formal derivation of that comes from starting with something that is known as the canonical ensemble, which is a very formal construct, the sort of thing a mathematician would put together to define a collection of things, right? So it is a collection of systems of molecules all in contact with one another under some particular constraints. We'll come back to that idea later. What we're going to do next over the next 2 or 3 videos is work to develop something that is closely related to this, something called the molecular partition function, right? When we think about the molecular partition function, we start off by thinking about the quantum states of just one single molecule. That is, at least in my view, conceptually simpler and is therefore a nice place to go from here in the development of things. And so in the next segment, we'll take up the beginnings of the molecular partition function. We'll start off by looking at translational motion, and then we'll subsequently come back and look at rotation and vibration and other forms of energy to get all of those accounted for. Thanks.